Okay, in this lecture, we're going to cover the first part of our section 2.7 material on cylindrical and spherical coordinates. So if we think back to our chapter 1 material, we had talked about polar coordinates, and we saw that points in the plane, in the xy plane, could be described using either the rectangular coordinates x and y, or polar coordinates, which were given by a pair r and theta, which had some geometric representations. So in this section, we're going to talk about alternative ways to represent points in space. Instead of using the rectangular coordinate system, x, y, z, we can use one of two other coordinate systems known as the cylindrical or spherical coordinate systems. So here we'll introduce the first of those. In the cylindrical coordinate system, a point P in 3 dimensions, so in space, can be represented by an ordered triple r, theta, z, where r and theta are the polar coordinates of the projection of our point P onto the xy plane, and z is the directed distance from the xy plane to the point P. So to illustrate this, here we've got some point that we're looking at in the first quadrant of XYZ space. So here I've got a point P plotted, and we can represent this point P either in its rectangular coordinates, x, y, and z, where x would be the distance we've moved along the x-axis, y, the distance we've moved along our y-axis, and z, the distance that we've moved vertically along the z-axis. Now, an alternative way to represent that point is as this ordered triple r, theta, z, where r and theta, we were told, are the polar coordinates of the projection of that point onto the xy plane. So if we take this point P and we project it down onto the xy plane, that is, if we just make its z coordinate 0, then this point would be the point r theta 0, where r and theta are the polar coordinates of that point in the xy plane. So recall here that r is the distance from the origin out to the point, and theta is the angle that we rotate by from the positive x-axis in a counterclockwise direction to get to that line segment which connects the origin to our point. So in cylindrical coordinates, r and theta have the same sort of interpretation that we're familiar with from polar coordinates in the plane. Now the only difference is now we have a third coordinate, which we're calling z, and z is the vertical distance that we travel from the xy plane up to our point. So, well, of course, that would be the same distance if we were to travel directly along the z-axis. So here, the z coordinate for a point in cylindrical coordinates is exactly the same z coordinate that we would have for that point if we were using the rectangular coordinate system. So what we are interested in doing for points in space would be to express them either in terms of rectangular coordinates, x, y, z, or cylindrical coordinates, r, theta, z. And it's useful to be able to convert from one representation to the other. So here I'll mention to convert from cylindrical to rectangular coordinates, we're going to use the following relations. So x, just as it was given in the polar coordinate system, would be r cosine of theta. Y, as in the polar coordinate system, would be given by r sine of theta. And we've already said that the z coordinate for the cylindrical system is the same as the z coordinate for the rectangular system. So z will be equal to the z value that we had in cylindrical coordinates. Now, if we want to move in the opposite direction, so let's suppose that we have rectangular coordinates and we want to convert from rectangular to cylindrical, then we would use the following relations. So just like we had for the polar coordinate system, r is given by the square root of x squared plus y squared. Tangent of theta is given by the ratio y over x, and then z, of course, is just z. So here we can see those same, or we can see the derivation of those formulas if we consider our triangle formed in the xy plane here. Well, our x coordinate is the length along this side of our triangle. Our y coordinate would be the length along this side. And then the hypotenuse of that triangle is r. So using the Pythagorean theorem, we have the following. Taking tangent of the angle theta there, it's defined as the ratio of the length of opposite over adjacent edges, so y over x here. And then z is simply equal to z. So let's look at some examples where we will convert a point in space from one coordinate system to the other. So in our first example, we are asked to find the rectangular coordinates, x, y, z, of the cylindrical coordinate, given as 2, 4 pi over 3, and 8. So recall, our cylindrical coordinate is given in the order r, theta, z. So those are the values we have here. So in order to convert to rectangular coordinates, we're going to use our conversion formulas where x is given by r cosine theta, y is given by r sine of theta, and z is z. So let's see what we have here. X would be equal to r, which was 2, times cosine of theta, which was our 4 pi over 3. So simplifying a little, well, we have 2, and then cosine of 4 pi over 3 is negative 1/2. So we have an x-coordinate of negative 1. Our y value is r, which was 2 times sine of theta, which was 4 pi over 3. So simplifying, we have 2 times sine of 4 pi over 3 is negative root 3 over 2. So our y value would be negative root 3. And then our z value is just equal to z, which we were given as 8. So this point could be represented in terms of rectangular coordinates, x, y, z, as negative 1, negative root 3, and positive 8. Okay, so two different ways to represent that point. Now let's look at another example where we're moving in the opposite direction. So here we are told to find the cylindrical coordinates, r, theta, z, of the rectangular coordinate. So that is the point given in terms of x, y, and z, which are root 3, negative 1, and 4. So using our conversion formulas here to find r, well, r is given by the square root of x squared plus y squared. So here we have the square root of, well, x was the square root of 3, so squaring it gives us 3, plus y was negative 1. When we square it, we have 1. So r is then root 4, or 2. Now, to find theta, we use the conversion formula that tangent of theta is equal to y over x. So in this problem, y was -1. We're dividing by √3. So we are looking for the angle theta such that tangent of that angle would be equal to -1 over √3. So here the fact that tangent of theta is negative means that we lie either in the second or the fourth quadrants. So to find these angles, well, if we're very familiar with the unit circle, we might be able to read them off immediately. If not, we can try to sketch reference triangles that have these desired side lengths. So here, tangent of theta would be defined by the ratio of the lengths of the opposite over the adjacent sides. So one option would be the triangle with the following lengths, say a y value of +1, an x value of -√3. Or in the fourth quadrant, we could have a triangle whose x value is +√3, y value is -1. In either case, our hypotenuse is 2. So the angles that produce these triangles would be given by, first off, this angle, which would be 5 pi over 6, or the angle here, which would be 11 pi over 6. And then the question becomes, well, which of these theta values do we want? So do we want the angle in quadrant 2 or quadrant 4? To determine that, we can look at our xy coordinates. Here, x was +√3, y was -1, which means that we're looking at the triangle that lies in that fourth quadrant. So the value of theta I want here was the 11 pi over 6. And then z is just equal to z, which was given as 4. So we can represent this point as the ordered triple r theta z, given by 2, 11 pi over 6, and 4. So a couple of examples of converting from one system to the other. And we can see here that this is really the exact same as the conversion between rectangular and polar coordinates in the plane, since our z coordinate is the same regardless of which system that we're using. So let's look at some other problems now that we know how to convert from one system to the other. So we can describe certain types of surfaces more easily in terms of cylindrical coordinates as opposed to rectangular coordinates. So to see that, let's consider some examples. Here we're asked to describe the surfaces with the given cylindrical equations. So in this first example, part A, we have 4r squared plus z squared is equal to 16. So to try to describe this surface, well, I might first convert to an equation in terms of rectangular coordinates. We're a little more familiar with the equations of surfaces in terms of x, y, and z. So in my equation, where I have this r squared, well, I know that r squared is given by the sum of x squared and y squared in terms of rectangular coordinates. So if I make that substitution into my equation, I have 4 times x squared plus y squared plus my z squared is equal to 16. So this, if I expand, could be written as 4x squared plus 4y squared plus z squared is 16. Or if we prefer to rewrite this slightly, we could divide both sides of our equation by 16, and I would have x squared over 4 plus y squared over 4 plus z squared over 16 is equal to 1. And we might recognize this equation as describing an ellipsoid. So this is a quadratic equation in terms of 3 variables, x, y, and z. So it describes a quadric surface, and the type of surface is an ellipsoid. Here we could even maybe get a sketch for this ellipsoid. So we have our x, y, and z axes. To visualize our ellipsoid, well, we can think about its intercepts. So its x and y intercepts would both be positive 2 and negative 2. And its z-intercepts, if we set x and y equal to 0, would be positive and negative 4. So in each plane, we have an ellipse. In the xy plane, it happens to be a circle since the intercepts are the same. In our yz plane, we have the ellipse that looks something like the following. And in our xz plane, we have an ellipse that looks like the following. So sort of a rough sketch here of our ellipsoid, but we can get a visualization of what this looks like. Now, in our part B equation, we have z is equal to r, so a linear function in terms of z and r for cylindrical coordinates. Let's see what this represents. So here, converting to rectangular coordinates, well, we know that the right-hand side of our equation, which was r, is equivalent to the square root of x squared plus y squared. So here we have, if we simplify, z squared is equal to x squared plus y squared. So we might recognize this as a equation of a cone from our previous section on quadric surfaces. So this again is a quadratic equation in terms of 3 variables, x, y, and z. The form of this equation suggests that we have a cone for our surface being described here. In particular, I need to be maybe a little bit careful. So here z was given by r, which was this positive square root of x squared plus y squared. So since z is the positive square root here, we're really referring to an upper half cone. So as a visualization here, from the xy plane, z, which is equal to r, we'll be describing the upper half cone, where our cross sections in any z plane are circles. So we will have a cone whose cross sections are circular. And the larger I take the value of z, the larger the radius of those Now let's look at some problems moving in the opposite direction. I mentioned that certain types of surfaces can be more easily described by an equation in terms of cylindrical coordinates instead of rectangular coordinates. So let's take a look at some examples of surfaces like that. So in this example, we're asked to describe each surface and then express the equation for that surface in terms of cylindrical coordinates. So looking at our equation in part A, we have x squared plus y squared plus z squared is 36. So we can recognize this as being the standard form for the equation of a sphere. So for the description of our surface, we have a sphere centered at the origin. That is the point 0, 0, 0 in space, with radius 6. So in general, the equation for a sphere, remember, had the form x minus x naught squared plus y minus y naught squared plus z minus z naught squared is r squared. So we have the equation of a sphere whose center is 0, 0, 0, or the origin. And since our right-hand side was 36, well, that's the radius squared, so our radius would be 6. So that is the first part of our problem here, is to describe our surface. The second part of the question asks us to express the equation in terms of cylindrical coordinates. So using my conversion formulas, well, I know that the sum of x squared plus y squared in terms of cylindrical coordinates would be r squared. So this equation could be rewritten as r squared plus z squared is equal to 36. So now this involves only the cylindrical coordinates r and z. So let's look at our part B equation. We have z equals 12 minus 4x squared minus 4y squared, which we might recognize as the equation of a paraboloid, an elliptical paraboloid. So let's take a look here. We could first maybe rewrite this. In the form, let's write it like this. 4x squared plus 4y squared plus z is equal to 12, or dividing through by 12, we would have x squared over 3 plus y squared over 3 plus z over 12 is 1. So this is more looking like the standard form for the equation of an elliptic paraboloid. So to describe this in a little more detail, we would have an elliptic paraboloid which is, or with its axis about the z-axis, since z was the only variable not involving a square here. We can even kind of visualize this. So thinking about traces of this surface, we see that if x and y are both 0, then z is 12. So let's see if we can sketch this as well. A little review on our quadric surfaces. So when x and y are 0, z is 12, so our intercept along the z-axis is 12. And the larger that I make the value of z, I could see, or the smaller that I make my value of z, I can see that my ellipses will be larger. So this is like a downward opening paraboloid. Where these little cross sections are ellipses. So a little crude sketch here, but we have a paraboloid opening downward with vertex at 0, 0, 12. So this would be a description of that surface. And we want to rewrite this in terms of cylindrical coordinates. So let's take a look at this. We had the equation z is equal to 12 minus 4x squared minus 4y squared. So if I factor out a negative 4 from those terms, I'm left with x squared plus y squared. So using the same conversion formula as in part A, well, I know that x squared plus y squared in terms of cylindrical coordinates is just r squared. So this would be an equation for that same surface in terms of cylindrical coordinates. So in our last part, part C, we have z is equal to the square root of 3x squared plus 3y squared. So if we were to factor out a 3 from each of those terms, we have the root of 3 times x squared plus y squared, which is the same as root 3 times the square root of x squared plus y squared. So we could recognize this as being the equation of a cone. So here we would have a cone sort of centered about the z-axis. Here, since z is defined as terms of a positive square root, again, this is sort of the upper half cone centered about the z-axis. So where our cross sections are circles. So that would be a description of our surface, and then rewriting the equation for this surface in terms of cylindrical coordinates, we would have z is equal to the square root of 3 times the square root of x squared plus y squared, which is equal to just r in terms of cylindrical coordinates. So we would have z is equal to root 3r for our equation of this cone in terms of cylindrical coordinates. So we see for a few of these examples, equations of, say, spheres or cones or some portion of a cone, or maybe paraboloids. If we convert those equations into equations involving cylindrical coordinates, they might have more simple representations in terms of cylindrical coordinates as opposed to the rectangular coordinates x, y, and z.